In this video file, I'm hoping to explain some of the first principles of probability using some examples, and hopefully this video file will help you to complete homework 9 uh, successfully. Okay, so let's have a look at this example. It says you toss a coin and randomly select a number from 0 to 9. What is the probability of getting tails and selecting a 8? Alright, so now notice we have two experiments here. One is tossing the coin and the other one is selecting a number from 0 to 9. So first you would write the sample space. So from the sample space we can using the sample space we can find the probability. Okay, now you also need to remember that the probability is a number between 0 and 1. So you cannot have a number bigger than 1 for probability or a number less than 0. Sometimes I've noticed some students use a percentage. For example, if somebody says the probability of occurring this event is 25%, that is a wrong statement. Okay, so you cannot use percentage format for probability. Probability is a numerical value between 0 and 1. Okay, now let's go back to this example. So we have two experiments here. One is the tossing the coin. So if you toss a coin, you have two outcomes, right? So okay, so let me okay, so you have toss the coin. Okay, the coin. Okay, you can have either head or tail, and then you are selecting a number from 0 to 9. Okay, so what are the possibilities? So you can, the second experiment, you can either select 0, 1, 2, 3, 4, 5 and so on, right? 6, 7, 8 and 9. So you can select any of these 10 numbers. Alright, now so what the sample space looks like. Okay, now first as you get comfortable with the concepts, of course you are welcome to write the answer straight away, but since I'm just introducing this section for the first time, I would like to explain this problem using first principles, which is using the sample space. Okay, now so the sample space consists of a set of all possible outcomes. Okay, now what are the possible outcomes? So what type of outcomes you can expect when you toss the coin and select a number from 0 to 9? Okay, so what are the outcomes? You can select there's a possibility of getting a head and selecting a number 0. That's a one possibility. Or head with 1 is another possibility, or head with 2 is another possibility, head with 3 and so on, and head with 9. And then similarly you can have tail with 0, tail with 1, tail with 2 and tail with 9. Okay, right, now so totally how many possibilities here? So totally there are how many outcomes? So there are 10 outcomes here, there's another 10 outcomes there, so there's a 10 here and there's another 10 there, so the totally we have 20 outcomes. Okay, now you can easily find out the number of outcomes by multiplying the number of outcomes of each of the experiment. Now in the first experiment you have 2 outcomes, and in the second experiment you have 10 outcomes, and if you multiply the two numbers you will get 20 the same way. Okay, now so we found the sample space. Now think about this. Now see, each and every outcome is equally likely, right? So if you randomly select any of the outcome out of these 20 outcomes, any outcome can be a possibility. So each and every outcome is equally likely. Equally likely means any outcome can occur with equal probability as of any other outcome. Okay, now since they are equally likely, we can use the classical approach, which is the theoretical probability, sometimes people call it. Okay, so what's the theoretical probability? The definition of theoretical probability is, well, probability of an event equals to, you have a ratio at the denominator is number of outcomes in the sample space okay, and the sample space, this is the sample space. Okay, so that's what we have found, and the numerator is, well, we are looking at the probability of A. Now out of that many outcomes in the sample space, how many outcomes are favorable to the event A? Okay, number of outcomes in favor of A. Okay, so basically you have to count number of outcomes in the sample space which are favorable to A. Right, so for this example, so we have to find out the probability of, what is that, getting a tail and selecting a number 8. Alright, so the denominator is, well, is 20 because the number of outcomes in the sample space is 20. That's the sample space, right? And then out of this sample space, how many outcomes favorable to T with 8? Okay, so T with 8, so there's T with 8 here, right? So that's the only outcome that is favorable with T and 8. So just one. Okay, so the probability is 1 over 20. So since these answers are given in the decimal format, so let's divide 1 by 20 and see what we get. Okay, which is 0.05. so the answer is first one. Okay, right, now next I want to consider number 3. Well, this is the one. Okay, so we have, okay, 15 of the 10 digital video recorders in an inventory are known to be defective. Okay, so 15 out of 100 are defectives. What is the probability that you randomly select an item and that happens to be not defective? Okay, so for the second question, okay, now let's see, so let's see number of defectives. Okay, items. So what is the number of defective items? It is 15, right? So then what is the number of not defective items? So how many? So the totally we have, they have 100 DVRs, so out of 115 are defective, so the non-defectives are 100 minus 15, which is 75. Okay, right, now now if you select one of them randomly, what is the probability of that selected one happens to be not defective? Okay, now remember, you are selecting one from 100 items, right? 100 DVRs. So so the probability that the selected one is not defective, okay, is, okay, now first you need to look at the sample space, right? So sample space, well, you have to pick a video recorder from 100 video recorders. So any of those 100 video recorders are possibilities, right? There's a possibility of selecting any of those 100 recorders. So the sample space contains 100 outcomes, right? So because any of those 100 DVRs can be selected. Okay, now the numerator, okay, and how many out of 100 are favorable for not defective? Okay, so 75. So 75 goes on the top. So the probability is 75 divided by 100, so which is 0.75. So let's type this and see. So it's 0.75. Okay, what is oh, I think we made a mistake because my calculations, yeah, because this is, I see that, so 100 minus 15 is not 75, it is 85. Sorry, it's been a long day. So it's 85, so 100 minus 15 is 85, so it's just 0.85. Sorry about this. So this is 0.85. There we go. All right, good. Okay, I hope I have not haven't confused you so far. All right, now next I want to discuss number 6 in your homework 9. So let's pick number 6. Okay, now here we have a table. These type of tables are called contingency tables. Okay, because this table contains 2 rows and 2 columns. So such tables are called contingency tables. Okay, right. So they are called contingency tables. Okay. Anyway, so let's have a look at this question. It says refer to the sample data for pre-employment drug screening shown below. If one of the subject is randomly selected, what is the probability that the test result is false positive? Okay, what does it mean by false positive? False positive means, okay, let's see. Okay, let's try to understand this this whole the data set. It says, okay, a subject uses drug. Okay, so subject, so the subject is truly using drugs. Okay, first row is the number of people who truly uses drugs. Okay, and then the second row represent the number of people in the experiment who did not use drug, or who truly not using drugs. Okay, now the first column, okay, says positive test results. Okay, now when these subjects are subjected to the drug test, well, the drug test happened to produce positive results. Okay, now here this 46, the 46 represent, what is this 46? How do you explain 46? 46 means well, the subjects truly uses truly use drugs, and the test positively identify them as drug users. Okay, 46 of the time this particular drug test identify correctly as the subjects are drug users. Okay, and here 19, this 19 represent what? How do you explain this 19? Well, this experiment falsely identified these 19 people because as drug users, but the subjects were not really drug users. Okay, so this 19 is a false identification. Okay, now the second column is negative test result. Negative test result means, well, this test says these subjects are not drug users. Okay, so this 9 is, well, it's a false identification, right? These 9 guys actually drug users, but the test failed to identify them as drug users. Okay, so these 34, okay, so these 34 correctly identified as not drug users because they did not use drugs, and the test correctly identified them as not drug users. All right, so that's how you can explain this contingency table. Okay, now let's see the probability. Okay, so what is this probability? Say we want to find out the probability of false positive, right? False positive means they are not using drugs, but the test indicate they are drug users. Okay, so how many false positives here? So how many false positives? So 19 false positives, right? False positives. See, positive, but they are not drug users. So 19, right? Now remember, the experiment is if one of the subject is randomly selected. So totally how many subjects they have? Okay, here we have let's see if I may draw it. Okay, so this is what the this contingency table looks like. You have okay, so drug users, right? Drug users, and not drug users. Okay, and then I'm just going to summarize this whole thing. Okay, and then here positive results. Can I use this positive here? Positive and the negative. Okay, all right, now we have, so this is basically what the table looks like. So you have 46 here true positive, and you have 19 false positive, and then you have 9 false negative and 30 for true negatives. Okay, now see, one of the subject is randomly selected, right? One, so out of how many? So totally there are how many? So totally there are, okay, here you have, okay, how many drug users? So 46 plus 9 is what? 55. So there were 55 drug users in the experiment. And how many non-drug users? So 19 plus 34, what is that equals to? So that is 53. Okay, so 4 plus 1 is, okay, so totally how many? So totally we have 8, so 108. So they have 108 subjects, so they are actually selecting 1 out of 108 subjects, right? So the sample space contains 108 outcomes, right? Right now the probability of false positive, right? Now we have to figure out the numerator. How many out of these 108 outcomes are false positive, right? False positive, well, 19 false positive out of 108, so 19 goes up here, so the probability is 19 over 108. So we have to round off to 3 decimal places, so let's divide 19 by 108, and it is 0.176 should be okay. Okay, 0.176. There you go. All right. We have another part. Who would suffer from false positive results? So who would suffer? The person tested would suffer because he or she would not be suspected of using okay, false positive means they are suspected of using drug, but they are actually not using drug. So which one is the correct one? Because the person would be suspected of using drug when in reality he or she does not use the drug. So this should be the answer. Okay, even though even though they are not in reality using drugs, but they happens to be tested positive. Okay, so the B. Oh, what did I oh goodness. Who would suffer from false positive? Let's see. Of using drug when in reality he or she does not use drug. False positive. Oh, what is the correct answer? Okay, it says it's not the employer, I'm sorry, it's the employee, right? So yes, yeah, I think it's C. It's the person. It's a sample data from pre-employment. It's not the employer, it's the employee, right? So because he or she would not, okay, would be subjected. Okay, it's not D. I think the person tested would suffer because he or she would be suspected of using drugs when in reality is not really using drugs. Again, the reason the B is not the answer, because it's not the employer, right, that is subjected to this testing. Is the employees, okay, potential employees, okay, pre-employment. So it's employees, the person, so it's the D. There we go. Okay, and the next I would like to discuss number 7. Well, we have number 7 here. Okay, okay, again, and yet another contingency table. Okay, refer to the sample data for polygraph tests. Okay, the polygraph means is a kind of a instrument that sometimes catches liars. Okay, if one person of the test subjects is randomly selected, what is the probability that the subject is not lying? Okay, now again, so let's redraw this so that I could explain it better. Okay, now so positive results. So let's see, positive here. I'm going to use that row as positive row. This is the negative row. Okay, and then here subject did not lie during the experiment. Okay, did not lie, and then here the subject lied purposefully during the experiment. Okay, now here so this number 13 says, okay, so here positive, that means this machine, this instrument falsely identify these 13 many people as liars, even though they did not lie during the experiment. And then this 41 says, well, subject the instrument correctly identify these 41 people as liars. Okay, and then here 35 means, well, this instrument correctly identify these 35 people as not liars because they didn't lie, and it correctly identified. Okay, and then 13 says, okay, the instrument incorrectly identified these 13 as not lying during the experiment, even though they purposefully lied during the experiment. Okay, so totally how many in this experiment? Okay, so let's see, it's 13 plus 41, what is that, equals to 454. Okay, and then 35 plus 13 is, what is that, 48. Right, so the totally they have 12, this is 102 subjects. Okay, so the probability that the randomly selected polygraph test subject was not lying. Okay, so totally there are 102 subjects, so any of those 102 a possibility. So the sample space contains 102 outcomes. Now out of these 102 outcomes, how many were not lying? Okay, how many did not lie? So how many did not lie here? So 13 did not lie and the 35 did not lie. So the totally how many? So 8 is 48. So 48 subjects did not lie during the experiment, right? The probability that the randomly selected polygraph test subject were not lying. Okay, they were not lying. So 13 here, 35 there, and then they all did not lie. So the totally there were 48 people did not lie. So 48 out of 102 is the probability. Okay, so let's we have to round off to type an integer or decimal round to 3 decimal places. Okay, so 48 divided by 102, so it is 0.471 should work. Okay, let's type it and see. 0.471, is that right? 471, yeah, I think this should work. Yes. Okay, this part is the result close to the probability rounded to 3 decimal places. Oh well, of 0.471 for negative test result. Okay, Let's see, is the result close to the probability rounded to 3 decimal places of that, which is what we got previously for negative test results. Okay, let's find out um, let's find out the probability of getting negative test results. Okay, so let's go back here. It's because it says about negative, is this probability 0.471 is close to negative probability of selecting a negative test result. Okay, so negative test result, I'm going to use a different color. Okay, so negative, so totally how many negative test results? So 35 here and 13 there, so totally 48 negative test results out of 102. Right, which is exactly the same thing. See, the same thing, this is this, so it should be again 471. So the answer should be yes. Yes, because there is less than 0.05 absolute difference between the probability of true response and the probability of negative test results. How? Okay, probability of let me read this question real quick. Just give me 1 second, I'll be back. Well, I'm back again. It's kind of truly confuses the way one confuses the way they have worded these problems. And when you the funny thing is when you read the question, you actually don't really understand what they are asking. But if you read their possible answers, you can kind of get an idea what they are really asking about. Okay, now if you look at these four possible answers, they are talking about okay, it says absolute difference, so let's ignore that. It says the probability of true response, and the probability of negative test results. Okay, probability of true response is also 0.471, right? True response means that they were not lying, right? And then the probability of negative test result is also 0.471, right? Right, so this is negative result, so it's 48 over 102 is again 0.471. So the difference between true response, probability of true response, and the negative test result is pretty much zero, right? 0.471 minus 0.471 is 0. So is the result closer probability rounded to the negative test results? I think it is yes. We'll see and we'll check. Yes, because it's less than, well, I think it should be the answer because it's 0. Let's check. Yeah, I think honestly speaking, this question is it's a ridiculous one, I'm afraid. Okay, anyway, so hopefully you understand how you calculate probabilities when a contingency table is given. So that's the most important one part here. Okay, now next I would like to discuss this one, this number 8. Okay, let's see. Let's hope there are no confusion parts. Okay, in a test of gender selection technique, results consisted of 271 baby girls and 16 baby boys. Based on this result, what is the probability of a girl born to a couple using this technique? Okay, so let's find out that one first. Okay, let me pick okay, there we go. So it says this because of this technique they have resulted 271 baby girls and how many baby boys? Okay, 16 baby boys. All right, now now this is what the experiment resulted. Now out of how many babies? In other words, so total, what is the total? The total is, well, 271 plus 16 is what is that? It is equal to 287. Right. So in other words, out of 287 babies born due to this experiment, 271 happens to be baby girls and 16 happens to be baby boys. Okay. Um, okay, what is the probability that the girl will be born using this technique? Is approximately. Okay, now we know that as a result of this gender selection technique, um, the babies, the 287 babies born, out of 287 babies born, 271 were baby girls and 16 were baby boys. Okay, now using this experiment, we are going to we need to approximate the probability of having a baby girl if a couple undergo this gender selection technique. Okay, right, now this is the data set we have. Now using these numbers we are approximating the probability. Now remember, this couple doesn't know whether they are going to have a baby girl or baby boy, which this event does not happen. Now we are going to approximate the probability of this event based on the past result. What is the past result? The past result says out of 287 babies, 271 were baby girls, and the 16 were baby boys. So we're going to use this result to approximate this future event. Okay, so we have 287 is a sample space. Out of 287, 271 were baby girls. So the probability that the next baby is a baby girl is 271 over 287. Okay, so we have to find the decimal form, which is 271 divided by 287, round off to 3 decimal places, which is going to be 0.944. Okay, let's type it and see. 0.944 works. Okay, does the technique appear effective in improving the likelihood of having a baby girl? Okay, 0.944. So what do you think? Okay, now if a couple undergoes this technique, and if that couple wishes to have a baby girl, there's like 90, almost like 94 chance of seeing their baby as a baby girl, right? So now that's a quite high probability. So the answer should be okay. So let's see. It can appear to be effective in improving the likelihood of having a baby girl. So let's see. Yes, so it is correct. Okay, now now I wanna tell you a little. Let's go back to the previous question. I wanna tell you something about this experiment. Now let's say if you just forget this problem, or let's see. Let me pick a new page. Okay, this is quite important one. This is called rare event rule. Rare event rule. Okay, so if a probability of occurring an event is less than or equal to 0.5, okay, if a probability of occurring a certain event is less than 0.05, then we say that event is rare event. A rare means most likely that event would not happen. Right, now let's see, now say this technique, for example, this gender selection technique, using this gender selection technique, so somebody found out that the probability of having a baby girl is 0.84. all right. This is a different experiment. Let's see, the probability of having a baby girl happens to be 0.84. Now, is this probability is high enough to conclude that this technique is a successful technique producing baby girls? So what do you think? Even though numerically it's kind of higher, but it's not high enough in terms of probability, because now if the probability that to have a baby girl is a 0.84, then what is the probability of not having a baby girl, having a baby girl? Okay, what is that equals to? If the probability of having a baby girl is 0.84, then the probability of not having a baby girl is 1 minus 0.84, which is 0.16. okay, in other words, there's like 0.16 chance of not having a successful result. What is, if you define the successful result as having a baby girl? So not having a baby girl, the probability is 0.16, right? So in other words, there's like 0.16 probability of having a not successful result. Now is this a big error or a small error? Right, now that is determined by this principle, rare event rule. Okay, now if you look at the error, so error is 0.16. okay, remember your desired result would be having a baby girl. Now having a baby girl, the probability of having a baby girl is 0.84, and the probability of not having a baby girl, which is an error, is 0.16. right, now is this error big enough? If this error is small, then we can say the technique is successful, but 0.16 is bigger than 0.05. It's quite big, so therefore a probability of not having a baby girl is quite big. Therefore not having a baby girl is not a rare event. Okay, in other words, it is not rare that the experiment produce an undesired event. Okay, so therefore we say this technique is not successful. Okay, so remember this is the rare event rule. But for this example, well, 0.944 is almost like 0.95, very close to 0.95. So the rare event, you can consider it as a rare event. The rare event means not having a baby girl, because if you do 1 minus 0.944, it's going to be like 0.06 something, very close to 0.05. So you can consider the error in this experiment with these numbers as rare, so therefore it is a successful technique. Alright, now next I would like to discuss number 9, the next one, this one. Okay, now let's see, in a survey 163 respondents say that they never use a credit card. Okay, and 1236 say that they use it sometimes, and 2830 say that they use it frequently. What is the probability that the randomly selected person uses a credit card frequently? Okay, so we have quite a bit of numbers here to deal with. Okay, so let's see, we have 163 that they never use credit card. Okay, never use credit card. So how many? 163. Okay, and then 1236 says they use it sometimes. Okay, use credit card sometimes. So how many? 1236. And 2830 says they use it frequently. Okay, use credit cards frequently. How many? 2830. All right. What is the probability that a randomly selected person uses a credit card frequently? Okay, so for this experiment, how many people have been used? Okay, so the total number of users, right? So total number of subjects. So what's the total number of subjects? You have to add these three numbers, right? So what is that equals to? So let's add these. Okay, cancel. So 163 plus 1236 plus 2830. So there are totally 4229 were subjected, okay, for this questionnaire. Okay, out of this many, how many said how many identified as frequent credit card users? So 2830, right? So the probability is 2830 over 4229. I think this should work. Okay, so let's see how many decimal places. 3 decimal places. So we'll divide. Okay, so 2830 divided by 4229. So it is 0.669 should work. Okay, let's type it and see. 0.669. Okay, let's check. Yeah, it works. Okay, is it unlikely for someone to use a credit card frequently? Is it unlikely? How likely this is, or is it unlikely? Okay, now unlikely means, okay, in other words, so we just want to find out whether this is a rare event. Is this a rare event? Okay, in other words, would it be would you come across somebody using credit card frequently? Is it a rare event to come across somebody who uses a credit card frequently? That's what you want to find out. Okay, so what do you think? So this probability is certainly bigger than 0.05, right? Remember, 0.05 is the rare event. So since this probability is bigger than 0.05, certainly this event is not a rare event. In other words, it is not a rare event to find out a person who uses credit card frequently. So is it unlikely for someone to use credit card? No, it is not, right? So it has to be B or D. Let's see. No, because the probability to use credit card frequency is greater than, so this should be the answer. It works. Okay, so that's it. And then well, I hope this helps you to answer these questions in homework 9 quite well. And if you have questions, please don't hesitate to contact me.